System models are excellent computer models to show dynamic systems like changes in population growth. They all start with the stock, which in this case will be population. And in the stock, we accumulate individuals or we lose individuals. And that's really the basis of a system model, is a stock. Now we have flows that go into it, like births. So I'm going to add a flow going into it. You just click and drag, and that's going to actually have a flow going out. That's not births. Births accumulate individuals into a population. So we're going to kind of drag that arrow out and then drag it back in until it lights up again. So now we have births which flow into the population, causing the population to grow. Let's change our population size to 200, and we'll change our births to 10. So each iteration or time step, 10 births flow into our stock of 200 individuals in our population. So each time step, you add 10, 10, 210, 220, 230. And that's the basis of our system model. We can then simulate it and see that at time step 1, there's 210, time step 2, there's 220, time step 3, there's 230, so on and so forth. And there's linear growth of the population size as we add a constant amount of individuals each time. We can also have flows coming out of our stock, in this case, death. Deaths will remove individuals from the population. And we can add our number of deaths to 10. So if we have 10 going in, 10 going out, that's going to keep a stable population size. Our population will remain at 200. As we add 10 births each time step, we remove 10 individuals with deaths each time step. So we add 10, remove 10, add 10, remove 10. And each time step, we do the exact same computation, and that will keep our population stable. We can simulate this also and see if our mental model agrees with our computational model. We can change the population size or birth rate to 11. When we change our birth rate to 11 and then run it, well, each iteration, there's one more birth than death. So that time step 1, there's going to be 201. And after 20 generations, there's going to be 210 individuals. Now, sometimes our population size affects how many births there are. More people there are, the more the birth rate changes. The more people are, the more the death rate changes. So our births are a function of our population size, and our deaths are a function of our population size. So we can change births to account for our population size. So we'll just get rid of, I mistyped population, so let's delete that. And as we delete that, we then select population and we're going to apply. So now births, number of births is based on population. And we see exponential growth. The more individuals, the more the population grows. Additionally, we can do the same thing for deaths. I like to drag these flows a little bit so we get to see the connection. We want to make sure we're using links instead of flows for this. So we're just linking the population to the deaths, and we're going to change our flow rate. Instead of being a constant at 10, we're going to change it to being based on the population size. Now, both births and deaths are a function of the population size. And what do you think is going to happen? Well, since they're both based on the same function, when we run this, they're at equilibrium. One thing I like to do, though, is add a variable so that I can vary my constant birth rate and vary my constant death rate. So what I'm going to do is I'm going to add a primitive, which is a variable, and I'm going to make it a constant birth rate. So for my model, what it was, my constant birth rate was just 1 times population. So I'm going to keep that just like it was and keep it at 1. And I'm going to do the same thing here, except now I need to add that my population size times my birth rate is my number of births. I'll do the same thing with deaths. I'll add a variable, which is not a converter, a variable, which is going to be my mortality rate or death rate, and it's going to be a constant. And I'm going to name it 1. And using a link, I'm going to connect that to deaths, making sure that my flow lights up. Add my mortality rate, have that be 1. And I'm going to change the number of deaths is going to be mortality rate times my population. And now I can run my model, and it should be just like before, because my population, my births and deaths are equal. It should remain stable. Now I'm going to add sliders in, so that allows me to perturb my simulation a little more easily. So I'm going to add a max and minimum to my slider, adjust my slider step, how much it changes by each time. And that will allow me to manipulate my model to understand the system dynamics a little more easily. So I have those sliders in. I actually want to change my population size also. So I'm going to add a slider for population size, and that's my initial population size that I'll be changing. And add max, minimum, I'm going to say 1. Now, I do want the population step size actually to be 1, because I don't want to start off with a half an individual. And I run this, same thing. But now I can change my birth rate, and I can run the model and see, exponential growth, because my birth rate was higher than my mortality rate. It grew exponentially. I can do the same thing where I can adjust my mortality rate. So I put my birth rate to 1.49, mortality rate is lower, but look, it went to negative. So I can change this actually. I don't want my population to be negative, so I'm going to go into my population size, scroll down, and I want to constrain the minimum. I want the minimum to be 0. So I have to change my minimum constraint, turn that on. And now when I run this, it runs to 0, but it says, uh-oh, the math I did went negative anyway. And the reason that is I had such a high difference between my mortality rate and my birth rate. Now that I make that difference a little more subtle, it will go down and go down to 0. So this is a great way. We can keep on running this simulation, and this is a great way just to see the system dynamics. You can perturb the birth rate and death rate and population size and see how that affects the shape of change.